Hey everyone, today we're going to start chapter 14.4, and this section's a little bit long, so we're going to cut it up into several days, and we're going to focus on this section about the change of concentration with respect to time. So the rate laws we have examined so far enable us to calculate the rate of a reaction from a rate constant and the concentration of our reactants. And these relationships can also be converted into other equations to help us show how the concentration of a reactant or product can be related to time. So we're going to look at first, second, and zero order overall reactions in terms of concentration with time. So, first order reactions. Remember, a first order reaction is one whose rate depends on the concentration of a single reactant raised to the first power. So, in our equation, first section, we learned that rate is equal to the change in concentration divided by the change in time. In the last lesson, we learned that we can come up with a rate law to show that the rate equals K, which is our rate constant, times the concentration of A to the first power, or it could be B to the first power. But we can actually change that equation to one that expresses time. And in order to do this, we actually use a operation in calculus called integration. Now, not everyone in here has taken calculus and learned how to integrate things, so our book has already done it. I will give you these equations on your homework, and I will also give you these equations on your test. So you will not need to integrate them. They will already be given to you. So our equation for a first order integrated rate law is the natural log of our concentration at a specific time minus the natural log of our concentration at 0 time. So we usually call this our initial concentration. And this is all going to equal negative K. And so remember, K is our rate constant. And then T is going to be for time. If you remember in math class, natural log, if you subtract two natural logs from each other, you can also rewrite it as dividing them here. So let's focus. Why do we need to learn this equation? What does this equation tell us? How do we use it? Well, one thing to note is that for the integrated rate law, we can use it as long as any of the concentration units are the same for both our final concentration and our initial concentration. Given any of the following quantities, you can actually solve for the fourth. So I can give you rate constant, time, and initial concentration and ask you to solve for final concentration. Or I can give you initial concentration, final, and time and have you solve for my rate constant. So there's a lot of different ways that you can actually use this equation. And three that your book specifically mentions is it allows you to determine the concentration of a reactant remaining at any time after the reaction has started, the time interval or the amount of time required or needed for a fraction of a sample to react. So, how much time is needed for a reaction to even occur? And then the third thing is the time interval required for a reactant concentration to fall to a certain level. So, when is my reactant concentration lowered all the way to 0.1? So, we're going to actually use that first order rate law and solve problems with it. Here is our first example of a problem. It says a decomposition of a certain insecticide in water at 12 degrees Celsius follows first order kinetics. So that means we're going to be using that first order kinetics equation. So let's go ahead and write it down. The natural log of our concentration at 8 minus natural log of our initial concentration equals negative KT. And it says it has a rate constant of 1.45 years, so that's going to be my K. It's okay being in years because years is a unit for time. And it says a quantity of this insecticide is washed into the lake on June 1st, and the concentration was 5.0 times 10 to the negative 7th grams per centimeter cubed. Oftentimes you see concentration as molarity, but remember molarity is moles per liter. So it's okay to have grams per centimeter cubed because you're still giving a unit for quantity divided by a unit for volume. And part A is asking us to solve for what is the concentration of an insecticide on June 1st of the following year. So it's asking us to solve for the final concentration after a year. Knowing that information, my ln of AT is actually going to be X because that's what I'm solving for. I'm going to subtract it from the natural log of my initial concentration, which the problem gave us as 5.0 times 10 to the negative 7th. And this is all going to equal negative K. Remember from our problem, our K is this rate constant, and it says 1.45. And then for our time, it says the following year. Since our rate constant was given in year, it's okay for our time to be given in year as well. So I can just write 1 year here. From there, I can plug and chug into my calculator, and you can see that the ln of x minus, if I plug in the natural log of this value into my calculator, you're going to get negative 14.50865774 equals negative 1.45. Now, hopefully you guys recognize that I'm subtracting a negative, so this becomes an overall positive value. From there, I need to get natural log of x by itself, so I'm going to subtract by the 14.5086 on both sides of the equation. From there, I can get the natural log of x actually equals negative 15.95865774. Oftentimes, I see students get stuck on this part because they see that they have x by themselves and they don't know how to get rid of that natural log. Well, I want x completely by itself, so to undo a natural log, you're going to find the exponential button on your calculator, which is a little e. So if I do this to the left side, I must also do this to the right side. So the e button to the power of negative 15.9586. When you do this, it cancels out this natural log, and you get x equals 1.17285 times 10 to the negative 7th. Now, I do want to make sure I'm keeping my sig figs, so my sig fig should be 2 based on this 5.0. So I'm going to get 1.2 times 10 to the negative 7th, and I need a unit. Remember, concentration units must be the same. So if my concentration unit of my original was grams per centimeter cubed, that means that should also be the concentration of my final. So grams per centimeter cubed here. Let's get a little bit more practice with this. And here we have a part B. It's asking us to find out how long will it take an insecticide concentration to decrease to 3.0 times 10 to the negative 7th. Here, my initial concentration is staying the same, and my rate constant is staying the same. So as we get going, let's just go ahead and write that equation back down. Therefore, we have it. Again, just to reiterate, this will be given to you. I will not expect you to memorize these. So as long as you guys can pick it out and use it, you are golden. Here, it's giving me my final concentration of 3.0 times 10 to the negative 7th, unlike last time. So now we can just plug it in. We're going to subtract it from our initial concentration, which is the same as the last problem, 5.0 times 10 to the negative 7th. And this is going to equal negative k. Our k value did not change. And then time. That one is what we're solving for now, since it's asking for how long. From here, we're going to take the natural log of 3.0 times 10 to the negative 7th, subtracted by the natural log of 5.0 times 10 to the negative 7th. And when you plug that into your calculator, you get negative 0.5 1.08256 238 equals negative 1.45x. Now I do want x by itself, so I'm going to divide everything by negative 1.45, and you get your x equals 0.3529, but I'm going to keep it as 0.35 for sig fig purposes. And I need a unit for time because I'm asking how long. Since my rate constant is year, my unit for time would be year. So it takes about 0.35 years, so less than a year, less than half a year actually, for this insecticide to decrease in its concentration. So a couple things to talk about with first order reactions is for a first order reaction, we can actually take this and graph my natural log of A at a specific time, and it will give us a straight line with a slope of negative k and a y-intercept of the natural log of your initial concentration. Because this is set up in slope-intercept form where y equals your m slope x plus b. So again, my y is my natural log at a specific concentration. Here, my x is t. My slope would be negative k. And then, of course, my y-intercept would be natural log initial concentration. So oftentimes when you see this set up, you're going to see the natural log of my A concentration per time, and my negative k tells me my slope is going to go down. Again, this is going to yield a straight line. So if we look at this, both of these are yielding natural log. Notice that this one is a straight line when I'm giving the natural log. So this one is a first order. This one says that it's graphing the natural log of A, but notice this is not a straight line. So this would be considered not first order. So that's the easiest way to tell on a graph if it is a first order reaction or not. In terms of second order reaction, this is one whose rate depends on the reactant concentration raised to the second power, or the concentrations of the two reactants are raised to the first power. So here we learned that K of our concentration to the second power. This can be integrated through calculus, and the differential rate law is expressed as follows. Again, I will give you this rate law for you guys to use on your homework and your quizzes and tests. It is 1 divided by your concentration at a specific time equals KT plus 1 divided by your initial concentration. Just like first order reactions, we can actually give you 3 of these variables and you're going to be able to solve for the 4th. And also with this one, we can actually plot it on a graph and get a straight line. It says if the reaction is second order, if we plot 1 divided by our concentration of specific time versus t, this is actually going to yield a straight line. Note that if we set this up as y equals mx plus b, my slope will be a positive k, so it's going to slope upward, and my y-intercept is 1 divided by our initial concentration. So typically you're going to see a graph where you see 1 divided by the concentration of A over T, and since this is a positive k, you're going to see this slope upward. So here this is the natural log. We said in a couple pictures back that this was not first order. But if we actually graph that as 1 divided by the concentration, we'll see that we get a straight line, which shows that even though it's not first order, it is a second order reaction because I get that straight line with my 1 divided by my concentration of A. So here we're going to work an example problem where we use that integrated rate law. So like we did with the ones before, we're just going to go ahead and we're going to write out the equation. 1 divided by the concentration of AT equals KT plus 1 divided by the concentration of my initial. And our problem reads the reaction of nitrogen dioxide yields nitrogen monoxide plus oxygen gas follows a second order kinetics. So we know this is second order, so that's why I wrote my second order equation. It says at 300 degrees Celsius, my nitrogen dioxide concentration drops from 0.01 molarity to 0.0065 molarity in 100 seconds, and it's asking us to find the rate constant, which is K. So we need to go ahead and plug in what we know. So we have 1 divided by our final, which we're going to plug in as 0.00650 because that's what it went to. This is going to equal our K that we're trying to find. Here, my time is going to be 100 because I have 100 seconds, plus 1 divided by my initial concentration, which we see here as 0.0100. Here, you're going to go ahead and plug into your calculator and consolidate terms. So 1 divided by this, it comes out to be 153 equals 100. And I'm going to plug in x for k, so just to illustrate that, plus if you take 1 divided by 0.01, that actually comes out to be plus 100. We're going to get 100 to the other side. So you get 53.846138 equals 100x. And then what we're going to do is we're just going to get x by itself by dividing by 100. So we're going to get x equals. When I divide this, I want to make sure my sig figs are appropriate. So I should have 3 sig figs based on my number. So I'm going to put 0.538. Now it is asking for a rate constant, and it is second order. Notice I'm given molarities and second. So second order rate constant, M-1, S-1. And last but not least, we're going to learn about zero order reactions. A zero order reaction is one in which the rate of the disappearance of A is actually independent of the concentration. And the rate law for a zero order reaction is actually rate equals K. So the integrated rate law for a zero order reaction is as follows. Again, I will give this to you. This equation for a straight line. Note that if this was a straight line, we have y equals mx plus b. Note that my slope, which is m, is a negative here. My y-intercept is just going to be the concentration of my initial. So typically when you see this, you're going to see this planted as your concentration over time and this negative slope here. So here is an example of 2 decompositions. One is a zero order reaction, one is not. The one that is going to be a straight line when you just graph the concentration is going to be, this one is a zero order because it's a straight line. This one is not a zero order. Here we're going to go ahead and solve for our zero order problem. So you guys have one of these in your notes. It says the following reaction A yields B is a zero order in the concentration of A, and the rate constant is 0.039 molarities per second. The concentration of A was 0.3 molarity at 23 seconds. The initial concentration of A was blank. So here, let's just go ahead and write my equation first. And then we just plug in what we know. So we know that the concentration was 0.3 after 23 seconds. So I'm going to plug that in for my AT. So 0.30 equals negative. Here, my K value, it says my rate constant was 0.039. So I'm just going to go plug that in for K. And then here it says 23 seconds, so I'm going to plug in 23 there, plus my initial concentration, which is what I'm trying to find. So plus X. I'm going to go ahead and combine like terms. So 0.30 equals negative 0.897 plus X. Let's get X by itself by adding this to the other side. And when we do that, we get 1.197 equals X. Now I am going to round to 2 sig figs based on the numbers I'm given. So 1.2 equals X, but I do need a unit. So since my concentration was molarity, my initial concentration should also be molarity as well. Let me know if you have any questions, and I hope you guys have a great day.